Good morning, everybody. Today we're going to talk about MRI imaging, magnetic resonance imaging. You will understand later why we use the word resonance. Just some features. MRI imaging provides images of inside the body. It has no ionizing radiation, and it relies on some nuclei that behave like tiny magnets. It also makes use of radio frequencies, electromagnetic waves, and you need to know that the body lies, when we are doing the scan, lies in a strong magnetic field. Now, how does it work a little bit? Radio frequencies are sent in the body. The radio frequencies that emerge are detected, and then in a computer a picture is built up. Okay? Now, I'm going to continue with my lesson, but maybe it would be helpful for you guys if you just pause the video and then just make notes. Okay? So pause it and make some notes, okay? All right. Okay. Now let's talk about the principle working. Of nuclear magnetic resonance. Okay. First of all, we need to know that nuclei sorry about that, too much liquid. We get there. First thing, nuclei contain atoms / particles that have a spin. Yeah? Now, when particles in an atom, could be electrons, could be protons, when they have a spin, they cause a magnetic field. And they are acting like to behave as tiny magnets. Okay? Well, in the MRI specifically, we are studying the hydrogen atoms simply because hydrogen atoms are everywhere present in the tissues. Yeah? So, and what do we know about hydrogen atoms? They consist only of protons. and protons we know are positive particles. Okay? So when they are spinning around, they behave like tiny magnets. So let's see how that looks like. We have some hydrogen atoms in tissue randomly, and because they are spinning around, they behave like magnets. Yeah, North Pole, South Pole, randomly distributed. So when we just look at these atoms, or protons, yeah, aligned randomly, so overall there is no magnetic field. Yeah, so normally protons are aligned randomly. Okay. Now we're going to look what is going to happen when we put these protons in a magnetic field. Yeah, in a strong magnetic field. Here we have a North Pole. Here we have a South Pole. Here again we have our protons. And how they're going to align? Well, they're going to align according to the magnetic field. Okay? So, we say protons are aligned in a magnetic field. Now, you can imagine that it's not easy to do this, so we need a very strong magnetic field. Okay? And we're talking about a magnetic field of around 1.5 Tesla, which is really strong. Yeah? So this is our external magnetic field. Okay, so again, a little bit in review. Protons, when they are spinning around, they create, like on a particle base, they create like tiny magnets. Yeah. In our body, well, obviously, all these particles are differently distributed, so when they are not in a magnetic field, they just have a randomly pattern. However, when we put the protons, which is already available in all tissues, and we put an external magnetic field over the tissue, then the protons are going to align according to the magnetic field. Okay? Again, I would say pause the video and make some notes. If we look a little, when we have a closer look to the protons, we will see that it does not completely align to that magnetic field. It is like rotating around the direction of the external field. So we say a proton is not aligned itself along the external field, but rotates around the direction of the external field. So, well, it is a kind of way aligned to the external field, but it also makes like a rotational movement. Yeah? If we look at our proton, proton is spinning around. It has aligned somehow along the magnetic field, but because of the spinning, it's like spinning around here. Yeah? It's like, remember that small toy, maybe, I do not know exactly the English name, but something that you throw on the floor and that's spinning and that's like moving up sideways. Yeah, we call this a gyration or gyration action. So this action is called this gyration action. I should better say it like that. Is called precession. Yeah, you need to know the word and you need to explain what we mean by precession. Okay? Now I'm going to show you a small video how precession more or less works. Okay? So make a small note of this, pause the video, right? Turn on the light so you can see better, hopefully. Just 1 second. Maybe a little bit more now. Okay.
And possess a spin. Into this, they have a magnetic field and can be seen as little bar magnets. And we put a strong external magnetic field, they align with it. Some are parallel, pointing up. Some anti-parallel, pointing down. The protons do not just lie there, but precess around the magnetic field lines. And the stronger the magnetic field, the higher the precession frequency, a relationship that is mathematically described in the Larmor equation. Parallel and anti-parallel protons can cancel each other's forces out, But as there are more parallel protons on the lower energy level, pointing up, we are left with some protons, the magnetic forces of which are not cancelled. All of these protons pointing up add up their forces in the direction of the external magnetic field. And so when we put the patient in the MR magnet, he has his own magnetic field, which is longitudinal to the external field of the MR machine's magnet. Because it is longitudinal, however, it cannot be measured directly.
Okay. So this video is mainly to show you...
Protons have a positive charge and possess a spin.
Okay.
Due to...
So this video is mainly to show you the precession action of the hydrogen atom. Yeah? Okay. Right. So in the video it was mentioned already the Larmor frequency. Yeah? Okay, so remember we talked already about centripetal motion, so there are some things that will be familiar for you. So the angular frequency of precession is called the Larmor. Larmor frequency. Wow. Okay. So, as I said, the Larmor frequency depends on the magnetic field density be 0, yeah, and the gyrometric ratio. Okay? Yeah. So the stronger the magnetic field, the faster the protons will spin. I would say better, faster the protons, as we say, spin, but better say precess around it. Okay? Obviously, you know physics, formula. So W equals to the gyrometric ratio and the magnetic field, or magnetic flux. That's magnetic field density. Sorry. Yeah. The Larmor frequency, we see that already. Remember from centripetal circular motion. It is measured in rad per second. Yeah? We see this? Does it look familiar? Strictly spoken, it is actually the angular velocity. Yeah? So Larmor frequency measured in rad per second. Okay? we know that the ratio of the barometric ratio for protons is minus 2.68 times 10 to the power of 8 radians per seconds times Tesla. Yeah? So now we can determine the frequency. Yeah? F0. Okay. So we can use U0 is 2 pi F0, okay? And this should be a familiar equation, okay? So now we can combine both formulas, yeah, and find the frequency, okay? Now, as I said before, we use a very strong field, and in most cases we use a field of 1.5 Tesla, which is very strong. Now, combining these two will give us a formula or finding the frequency, yeah, of the around, we get F0 is y B0 over 2 pi. The barometric ratio is given 2.68 times 10 to the power 8. The magnetic field is given 1.5 Tesla, so we can fill in F0 equals 2.68 times 10 to the power 8 times 1.5 divided by 2 pi. And when we make a calculation, we get around 6.4 times 10 to the power of 7 hertz, which is equal to 64 megahertz. Well, if you know electromagnetic wave, the frequency of the electromagnetic waves, this lies in the radio frequencies. Yeah? And that's how, remember we talked about that we use RF radio frequencies. Okay? And this is important, yeah? Because now we come, how can we actually make use of resonance? Okay? So, make a note of this, pause the video, and then I will continue. Resonance. Okay. What about the resonance? Remember, that was the natural frequency of vibration. Now remember, when we put a magnetic field of 1.5 Tesla over the protons, it will spin around with a frequency of exactly 64 megahertz. Yeah? So this is also, we call that the frequency of absorbing energy. And now here comes the interesting part for the MRI. Okay? So what the MRI does, it gives pulses of these natural frequencies. Yeah? So that is the same frequency of the precession that we discussed. Yeah? So important to know that in MRI, pulses, and I put an emphasis on pulses, yeah, pulses of RF waves, radio frequencies, yeah, and these are the same frequencies of precession, yeah, and these frequencies are exposed to the proton. Okay? So what will happen if you use the same natural frequency, which is the frequency of precession? Well, you get resonance, and that means the protons, they're going to absorb that energy. Yeah? So protons absorb RF radio frequency, energy. Yeah? And what will happen with the proton? Proton flips up to a higher energy. Okay? And this is what we call the nuclear magnetic resonance. Okay? Alright. Now, I told you that we are going to give pulses to the proton. That means it's like we're switching it on and then we turn it off. Yeah? So, RF waves are turned on and then switched off. Now what's going to happen when you switch off? That means the protons go back to their original state. Yeah? And they will gradually relax. So protons will gradually relax. Okay? During this relaxation process, they release energy. Yeah? So, during relaxation, protons release their excess energy in RF waves. Yeah? These waves, they are detected So when we go back to the beginning, we said radio waves are going inside the body with pulses. Then there's a relaxation time. During the relaxation time, radio waves are released as an excess of energy, and these radio waves are detected. Okay? Now, what does it have to do with the different tissues? I'm going to explain you that now. Yeah? So make a small note. And we continue. Okay. Now I'm going to look at the rate of relaxation. And the rate of relaxation actually tells us something about the environment of the proton. That is very important. Yeah? So, environment of the protons are the tissues. Okay. Okay. So let's hear. Have again our proton spinning around. Then we get first phase when a radio wave comes in. We get resonance. So increase energy, so it's going to flip in one way or another, so we get absorption, proton going to flip, then there is no pulse anymore, and then we get relaxation, and the proton is going back to its original state. Now remember, there's always still this strong magnetic field, okay? They are still in the strong magnetic field, but we're going to give them the radio pulses, okay? Right. So what is going to happen here is energy is released over a certain amount of time. Yeah, energy of protons. Okay? And now the interesting part is, how do we see the different tissues? And this actually is related to the relaxation time of the protons, yeah, in different tissues. Each tissue, the relaxation time is different. Okay? So, for what are the tissues? Relaxation time is several seconds. For fatty tissue you find mainly in the white part of the brain, yeah, and they have like a relaxation time of several hundreds of a second. And when we look at cancer tissues, yeah, they have like a relaxation time that is intermediate. Okay? Yeah? So, we can distinguish the different tissues with the different relaxation times. So, we can distinguish different tissues according to different relaxation times. Put that in red so you can read it better. Yeah. Relaxation times. Different. Okay? This is how to distinguish the different relaxation times. Okay? Make a note of this and then we continue. So, in review, protons are exposed to radio frequencies. This is the natural frequency of the proton in an external magnetic field. The proton is absorbing this energy. When the radio frequencies are turned off, the proton releases energy in the same radio frequencies, more or less. That energy is being detected, and we are looking at the relaxation time of the different, and the relaxation time depends on the environment of the environment. So in this case, that is the tissues, relaxation time, sorry. Okay. Now, just check if the video is still working. Because it's a long video and do not know how long it records. Okay, it's continuing. Good. Alright. Now we're going to look at some features of the MRI scanner, and you will find this picture on page 524. These are the main components of the MRI scanner, and you can see it here. Okay, just check. I'm not going to draw it on the board. I'm going to tell about the features. Okay. Now, what do we have? First of all, when we look at the MRI scanner, it has a large superconducting magnet. Remember, we are really going to use a very strong magnet, yeah, and this produces an external magnetic field over the body. Okay, yeah. These magnets are getting very hot, so that means they need to be cooled by using liquid helium. Yeah? Alright. Then we have an RF coil. Yeah, this one transmits RF to the body. Okay, and it goes in pulses. Then there's another RF coil, and this one that detects